This is Taeyeon Park and Soyeon Park. We're gonna introduce algorithm math. The sequence of presentation is as follows: understanding of algorithm conditions, importance of math in AI, mathematical principle of algorithm optimization theory. An algorithm is formalized expression of a procedure or method for solving a problem so that the computer can follow it. It is an expression derived from the name of Muhammad al-Khwarizmi, a 9th-century Persian mathematician. To solve the problem, the accuracy and efficiency of several algorithms are evaluated and the optimal algorithm is selected. Algorithms conduct computation, data processing, or automated inference. From now on, I'm going to introduce algorithm conditions and accounts. Input. There are 0 or more externally provided materials. Print. It must produce at least 2 different results. Clarity. The execution process must consist of clear and unambiguous commands. Finality. It terminates after executing a finite number of commands within a finite amount of time. Efficiency. All processes must be clearly executable, verifiable. Mathematics is important in the AI field because the entire process of constructing and learning AI models from data input to output is expressed mathematically. Data and models are expressed in vectors and metrics that appear in linear algebra. AI is a probabilistic model, and optimization techniques that include the concept of differentiation are used for AI model learning. If you want to implement a model that fits the problem you want to solve, you must know how AI models work. Even when improving the performance of an already implemented model, you must be familiar with the model. Mathematics is a powerful tool for better understanding AI. Now let's learn about the mathematical principle of algorithm. Linear algebra. Representation of data and models. One of the important elements in the field of AI is data. Just as people learn in their daily lives, AI models also need data to learn. The human brain can immediately understand various types of data, such as images, text, and voice. However, computers cannot do this, so when using data in AI model, the data must be converted into a format that the computer can understand. What computers can understand are numbers, but it is impossible to display complex data with a single number. Therefore, in AI, data is expressed in the form of an array of several numbers. Image data becomes a multidimensional array containing pixel values, and text and voice data also undergo processing and are expressed as an array of numbers. This array of numbers corresponds to the vector and matrix concepts that appear in linear algebra. Additionally, when data is expressed as a mathematical matrix, we can apply the concepts of linear algebra in the process of finding the optimal model to solve our problem. Therefore, expressing data in the form of an array can be said to be an efficient method both in theory and in actual implementation. Probability and statistics, AI as a probabilistic model. The theory of AI, especially machine learning, is based on the ideas of inferential statistics. The data we know is actually observed result from a specific probability distribution. For example, when tossing a coin multiple times and recording results as heads and tails, the recorded data is the result extracted from a probability distribution, where the probability of heads and tails is 1/2. Similarly, people's heads also follow a certain distribution, and people's actual head data can be thought of as randomly drawn samples from that distribution. Given the data, estimating the specific probability distribution the data follows is core goal of inferential statistics. Because each machine learning model represents a specific probability distribution or boundary between probability distributions, The concept of probability is included in defining and training a machine learning model. The type and structure of the model determines the form of probability distribution, whose details are determined by the parameters of the model. For example, let's say we train a model with data that follows a normal distribution. Then we must select an appropriate model structure to make the probability distribution. Represented by the model on normal distribution, and use the given data to change the model's parameter values to adjust the mean and standard deviation of normal distribution to suit the data. Hyperparameter, a term that frequently appears in the field of deep learning, is also concept that corresponds to model structure. In the end, machine learning can be said to be a process of first defining an appropriate model structure and then finding optimal parameter values. Calculus for a better AI model. The data we observe contains a variety of errors. There are errors that can be reduced by humans, such as errors in measuring instruments and data lossing during communication, but there is also noise inherent in data. Therefore, even if data is observed from a certain probability distribution, not all data exactly matches that distribution. Additionally, it is impossible to estimate a probability distribution that fits all data exactly. Therefore, the goal of a machine learning model is not to create 100% chance of observing given data, but to maximize the probability. However, the loss function, a function that represents the difference between the model prediction results and the correct data of a model with many parameters, especially a deep learning model, is very complex. So, the optimal parameters cannot be calculated at once. Instead, we use a method of updating parameters little by little over multiple times. So, how much should each parameter be adjusted? The field of mathematics related to this problem is calculus. Differentiation is a concept that represents the amount of change in an output variable according to the amount of change in the input variable in a function. For example, in the machine learning, input variables can be thought of as data and model parameters, and output variables can be thought of as the model's prediction results. However, when training a model, the data is already given, so the data is not a variable whose value changes, and the concept of differentiation is used to calculate the relationship between the change in the parameter and the change in the predicted value. Since it is easy to calculate difference between the model's predict results and the correct data, we can use this error value and differentiation to find out how much the model parameters must be changed to reduce error.
Optimization theory is an academic area concerned with the problem of finding a solution that maximizes or minimizes within a set considering performance exponential function. Optimization theory is used in many areas, for example, financial engineering, control theory, and power systems. There are three types of gradient descent. These are batch, stochastic, and mini-batch. Batch is a method of calculating the slope using all data. The stochastic method uses only one data to train the artificial neural network. Mini-batch gradient descent can be seen as a combination of batch and stochastic methods. Next, I'm going to tell you about the specific characteristics of gradient descent. First is batch gradient descent. Batch gradient descent is followed by two steps. First, compute the slope that is the first-order derivative of the function at the current moment. Second, move in the opposite direction of the slope increase from the current moment by the computed amount. In this step, batch gradient descent is followed and data are analyzed. Next, there are many characteristics of batch gradient descent. From this following picture, batch gradient descent is commonly used for convex or relatively smooth air manifests. This picture is an example of cost versus epochs. Also, in batch gradient descent, all the training data is taken into consideration to take a single step. Another gradient descent is stochastic gradient descent. The picture shows stochastic gradient descent without momentum. Momentum is a term originally used in physics that refers to the tendency of an object to continuously change in one direction. It can be understood as power, driving force, momentum, inertia, etc. Stochastic gradient descent basically works almost in every situation. However, its updates can start oscillating. To solve the problem, it has been proposed the momentum technique, which can both speed up learning and increase accuracy. In this case, momentum is a way to average over our gradient descent. I will tell you about momentum technique related to that picture. Gradient descent does not exactly provide us with the direction in which the loss function is headed. Therefore, we might not always be headed in the optimal direction. This is because the earlier derivatives of the loss function act as a noise in the later stages of the updating weights. This causes slow training and convergence. To solve this problem, momentum technique appeared. Momentum technique helps us solve this issue of slow convergence. Consider a situation where a ball on a hilly turn is trying to reach the deepest valley. If the slope of the hill at some stage is very deep, then the ball gains a lot of momentum and is able to pass through slight hills in its way. As the slope decreases, the momentum and speed of the ball decreases. It comes to rest in the deepest position of valley. SGD, the stochastic gradient descent, considers just one example at a time to take a single step. Also, SGD is a way to tackle the way of batch gradient descent. It can be used for larger data compared to batch gradient descent. It converges faster than batch gradient descent. There are 5 steps of stochastic gradient descent. First, take an example. Second, fit it to neutral network. Third, calculate its gradient. Fourth, use the gradient we calculated in step 3 to update the weights. Fifth, repeat the steps 1 through 4 for the examples in training dataset. Lastly, there is mini-batch gradient descent. People call mini-batch gradient descent as batch gradient descent, but there are clear differences. MGD, mini-batch gradient descent, is a mixture of batch gradient descent and stochastic gradient descent. It uses a batch of fixed numbers of training examples which are less than the actual dataset and call it a mini-batch. The following picture is the way mini-batch gradient descent is followed. It is quite different from batch gradient descent. Batch gradient descent doesn't vibrate. However, mini-batch gradient vibrates. The reason for this is that MGD is more frequently updated. Also, mini-batch gradient batches are randomly selected. This is the proof that mini-batch gradient descent is mixed with stochastic gradient descent and batch gradient descent. There are 5 steps of mini-batch gradient descent. First, pick a mini-batch. Second, fit it to neutral network. Third, calculate the mean gradient of the mini-batch. Fourth, use the mean gradient we calculated in step 3 to update the weights. Fifth, repeat the 1 through 4 steps for the mini batches we created. Thank you for listening.